Hello, my name is Trevor Ablett, and I'm a PhD candidate at the University of Toronto. Today, I'm going to be presenting Learning from Guided Play, Improving Exploration for Adversarial Imitation Learning with Simple Auxiliary Tasks. The problem we investigated was the failure of AIL in a set of manipulation tasks. We hypothesized, and later demonstrated, that this resulted from a loop of poor exploration and deceptive learned rewards, leading to suboptimal locally maximal policies. Notice that in each of these examples, the policy may partially achieve the task, but fails before it is fully complete. We attempted to resolve this problem using expert-provided auxiliary task data for a set of 4 main tasks shown here at the top and 5 auxiliary tasks, common to all main tasks, shown at the bottom. To illustrate how a deceptive reward can cause AIL to fail, consider this toy MDP, representative of a stacking task. In the true MDP, rewards are accumulated for maintaining stacked blocks in state 5, but a large negative reward occurs for moving over top of the green block without stacking the blue block first. An expert demonstration is provided where the block is correctly stacked. As we show in our provided code, a policy learned with Q-learning and a reward based on the expert demonstration can incorrectly learn to jump from state 1 to state 5 due to the learned deceptive reward of state 5 even when the blocks are not stacked. In learning from guided play, we define several subtasks in a manipulation environment and then combine existing work in hierarchical reinforcement learning with off-policy adversarial imitation learning to learn multitask policies. Guided play takes on a dual meaning for our work. Guided expert play, in which an expert is guided to generate a multitask dataset via random sampling of high-level tasks, and guided agent play, in which an agent is guided by a learned or predefined semi-random scheduler to explore all auxiliary tasks in addition to a main task. One major benefit of this approach is that all auxiliary policies can learn from the full set of experience. This table summarizes the expert datasets, specifically the number of state action pairs that we used for our experiments. Multitask methods, including our method, were able to reuse auxiliary task data, indicated by bold letters in the table. To try and make a fair comparison, single task methods were given 6 to 7 times more main task data. Our results show that LFGP strongly outperformed all baselines on 3 out of 4 tasks, and that single task AIL failed on all tasks. Here's a video comparing the learning progression between LFGP and single task AIL. Notice that, even at only 200,000 steps, LFGP has learned reasonable policies for a variety of auxiliary tasks and performs far more diverse exploration of the environment overall. By 800K steps, LFGP has learned to stack, while DAC has learned a highly suboptimal policy. Here we show analysis of our learned policies. These diagrams display the learned policies for one slice of the environment with the blocks placed as shown. The LFGP policies have already made strong progress on all auxiliary tasks and the main task, while single task AIL, DAC, has made minimal progress on stacking. Similar to the previous video, these diagrams show the motion of the end effector for an entire episode at 4 points during training, demonstrating the high diversity of motion exhibited by LFGP. In this work, we show that adversarial IL can fail in manipulation tasks due to poor exploration and deceptive learned rewards. We resolve this using learning from guided play, in which auxiliary expert task data enforces exploration. As a bonus, this formulation allows for reusable expert data and potentially reusable policies. For future work, we'd like to investigate learning from final states only, or the possibility of transfer learning using common auxiliary tasks. I'd like to thank my co-authors Bryan and Jonathan Kelly. Feel free to check out our blog post or open source code.